This video is going to describe our quantum computing augmented reality app called MARVLS and the lessons that go along with it. So I first want to show you the lessons. So this is the front page and it shows the materials you need, including the smartphone, a merge cube template, and this is just what the icon looks like when you download it, and then the first screen. This first lesson is really just about bits. So right here, all students are doing is they're opening up their very first augmented reality scene and seeing a bit. The second part here is counting with binary numbers. So there's a table with numbers. There's some instructions about how students can operate the augmented reality scene. And there's some questions that they have to answer. And down here below, whenever you see this, this is navigation. So here it's showing you the ways to get to the two scenes. So I'm going to show you those first two scenes. Here, we're going to go to bits right here. We're going to go on off. So we see switches here. And there's some information that you can read. And then students can click on this button to see the AR scene. You point your phone at the bit or at the cube, and the cube is read, the image is read by the camera on the phone, and it recognizes it and tracks it. And so we can turn the bit on and off, and we just see it only has values of 0 and 1. And so just to understand what a bit is. So we'll go back and we'll count next in binary. So here we're just going to go here. Again, there's some more information. Click on this AR button. We can see 4 bits now. And now we can just add 1 and we can see how the bits change, right? And count, we can count all the way up to 15. And then it just resets to 0 and you can start again. Okay, so next we'll go to qubits. So learn a little bit about qubits. So the first um, lesson about qubits is, so I forgot to mention on the counting is we have a little bit of information about how you can convert a binary number into a decimal number. So there's some instructions, there's some questions, some examples, and so students can work through that. And now this next lesson gets into qubits. So what's the difference? How are they represented? And we talk about both the binary representation here, right? Like we had the switches as one example, and then for qubits, our representation is the block sphere. So they can learn a little bit about what that is. They also learn a little bit about ket notation. So the states of a qubit are 0 and 1, but those ket operators help us understand that it can be that can be a superposition of either one of those states. Then this is some instruction. There's some instructions here about the qubit scene. It tells them about what the buttons mean. So super means superposition state, and then measure means they're measuring it. And then it asks a few questions. Um, and then asks them to go into the MARVLS qubit versus bit scene, right? And change the state so they can compare the two. And right down here, we're seeing the navigation. So let's go in and look at that. So we're going to look at the qubit first. Right, so here we have the qubit. We can see the 0 and 1, and we can create a superposition. So you can see the block sphere vector is moving all around. It gives us percentages of the probability of it being in the 0 or the 1 state. And then we measure, and we can see the state collapses into the 1 state. And we can go again, superposition, 1 state again, 1 state again. It eventually does go to the 0 state. There we go, the 0 state. So let's go to now qubit versus bits. I'm going to turn this on again. So they can read about that, and then we can click on the AR button. And this is comparing. So you can see on the right, we have the bit, and on the left, we have the block sphere representing the qubit. So we can change state here, right? And so we can see when we change state, right, the bit stays as 0 or 1, but the block sphere, the qubit, can be in 0, 1, or any other angle, right? That represents a superposition of 0 and 1. Calculations. So this gives a little more information, talks about how they're different, how the calculations are different. And if we start out here, we can see that our initial um, input, calculation, and output is representing bits. So if we add one, meaning add a qubit, or I mean, add a bit, add a second bit, and add a third bit, right? We see that the input is 3 bits, our calculation is 3 bits, and our output is 3 bits. But now if we change the type, we'll go back to just 1 bit, and we look at qubits, we can see that if we have on the left on the input, if we have 1 qubit, right, then we know that we can have 2 states here, right? And so our calculation doubles, our number of calculations that we can do doubles, and our output still collapses into just one value. We can look at these and see like what they look like in 3D. We can now add one, add another bit, right? And this we see again, these our input is in a superposition of states, which means that there can be any combo of 0 and 1 for each bit. So we get, see, 4 calculations that can occur, right? Whereas when there was just bits, it was just still, again, one calculation, and our output collapses to just the value of each of the 2 bits. And then if we add another one, we see that we get up to, for 3 bits, we have 8 calculations that can happen at once. And so this is just to illustrate how quantum computing is pretty powerful, because the number of qubits increases our number of calculations exponentially. So we can go back. And for entanglement, let's look at the lesson for that. So we want to look at entangled bits, and what does that mean? So here we talk a little bit about what that means. Let me just pull up my little pointer again. Here's a description, here's some navigation information, and then it tells them what to look for. So one of the things that students do is they will um, select entangle. And so when entangle is selected, one thing will happen, and when it's not selected, another thing will happen. But each time they need to put their qubit into or qubits into a superposition, right? And when superposition is showing, it's in a superposition of states. And then when they click measure, that's when they'll see the measurement. And so they can select entangled or not entangled, and they can also select whether they want it to be the same or opposite. So let's look at that. So here we have our 2 qubits, and now we have this little menu where we can, so there we're going to measure, and we get the 0th bit. This one on the right is 1, and the Q1, the first bit, is down, so 0. So I can put it into a state of superposition, right? So we can see they're in a superposition because they're along the equator, which means they're 50% up and 50% down. And I can measure, so we get both down, put them in a superposition again, measure, up, superposition again, right? So these are not entangled. So there we see that they're just randomly going in, becoming 0 or 1. And so now if we want to entangle them, we're going to entangle them, and now we're going to measure. And so these should always match, right? So we're superposition, and then we measure down, up, down, superposition, and then measure. So now we're going to try the opposite state. So we're going to measure. We can see they switch, right? So if one is up, the other is down. So that's just showing how we can entangle qubits and what that means. Okay, so next we're going to look at spin. So spin is, let's look at the lesson for that. So this is still the lesson. I forgot to mention, this is the lesson that goes along with the calculations for qubits. Um, and so spin, actually, this was rearranged a little bit, but spin is a little further down. So right here. So this is our lesson for spin. You can see the navigation here, right here, right? And so do electrons spin? No, they don't really, but they can, because they can have some sort of electromagnetic wave applied to them. Um, but we can see here, we're going to apply an energy, and we can apply an energy and cause the spin state of an electron to change from down to up or up to down. And so we can see like what happens for higher energy, which we're representing with a blue color, because the blue is higher frequency and higher energy than, say, a lower energy. So we need a higher energy to go from down to up. versus would need a lower energy to go from up to down. And we also are going to show that that not only can we go from up to down using the very specific frequency, we also are going to show how we can use frequency and the pulsing of the laser to put it into a superposition state. So that's what this lesson, these 2 pages, oops, for this lesson, oops, okay, shows us. So it's asking us to change the frequency, to choose the whether the laser's on or not, whether to choose the up down or the down up state here, and whether to choose superposition. And then here we can see how to pulse when we get to superposition. And then students are asked to like draw what happens for the down to up transition and each of the other transitions. So let's take a look at that one. So here's a little bit more information they can read. And then here we have our electron, and it's in its lowest energy state, the down state. There's some information here about how to play in case they weren't sure. So just right in the game, they can read about that. It has a scroll bar so they can move around. We can close this, and then we can open up the buttons. So what this allows us to do is turn on the laser. So we can say the laser's on. We're going to choose the down to up transition. And so you can see we went to a higher energy color. And when the frequency gets close to the right frequency, you can see to indicate that the electron will turn that color, just to let students know they're, I don't know if this is going to let me use the pointer too, but you can see it just went from down to up. But let's just do that again. Let's just reset. I think we might have to see. Yeah. Okay, there we go. So it's down, and now we're going to drag this over. When we get close, it should turn purple, like the color of the laser. And now you can see it goes from that's in the down state, and now it's going to go into the up state. There we go. We can switch and try out a lower energy. So this is the up to down state, and you can see we're in the up state. We're getting close. We're getting red to match, and we're in the up state, and then we just went to the down state. And then for superposition, where we need to find where the right energy is. And so we can see, oh, it's starting to turn purple. So we must be close. And then you'll notice on the screen that this pulse button shows up. So right here, this pulse button, you can see right here, and that allows us to actually pulse the laser, right? So when we pulse the laser, it rotates that electron into a superposition of 0 and 1, right? So we can pulse again. So students are able to practice and see that it's not only the frequency and as well as the duration of the pulse determines the rotation or the change from up to down and down to up, as well as being able to having that combination of frequency and pulses allows us to put it into different superpositions as well. Okay, so now we're going to go to um, logic gates. So we have some qubit logic gates and a little bit of information, and we'll look at the lesson. So our lesson for the logic gates. So this is looking at just a single qubit and what a logic gate does to it. And we're just talking a little bit about the block sphere and what the gates do. And usually a gate is either going to change the state from 0 to 1 or 1 to 0, or change the phase, meaning put it into a superposition state. So probability of 1 and a probability of 0. So both are possible. And then also change the phase in terms of what axis we're going around. So in this example, we're using a NOT gate. You can see the blue gate there, and there's some questions about drawing the before and after for the block sphere and also the probability amplitude graphs for each of the gates. So that's the first part for a single qubit. And then if we want to have a 2 qubit circuit, we're going to look at the Hadamard gate, the NOT gate, and the control NOT gate. So we have a couple of examples. We have students draw the circuit to get more familiar with that, but then draw the before and after for each case. So let's get to the AR model so they can read about that there. And then here we have just 1 qubit. So we're going to turn that screen on, and this is shows what the register for a qubit and what that looks like. It shows the probability graph. So we see 100%. This qubit starts out in a state of 0. And if we add a NOT gate, we see that it changes both in the block sphere and in the probability graph. If we drag that off, it goes back to 0. The Hadamard gate is a gate that puts the qubit into a state of superposition, right? So it is equally likely to be in a 0 or a 1 state, and we can see that in the probability graph. And then the RY is a phase gate. And so that will cause the qubit to be in partially in a higher probability of state 0 and then a smaller probability of state 1, but both are possible. And we can see that happening right in both the probability graph on the circuit itself and on the block sphere. And so if we look at the 2-qubit example, here we've got 2 qubits, and what we're doing is we're going to put our circuit components, our Hadamard gate first, onto the Q0 register. We see both registers there for Q0 and Q1, and we can see the probability amplitude here is showing us that both of the qubits are in a state of 0, 0. So 0 on the right is the Q0, and 0 on the left is, when we look at these two numbers, is Q1. So that's what we're going to want to be looking at. So what we're going to do is we're going to drag this Hadamard gate. I don't know if it's going to let me do that. So drag the Hadamard gate up, and we can see now Q0, the second number, it has a probability of being in both states. And we can see that too in the block sphere. And then if we decide to add another Hadamard gate, but we'll add it to Q1, this will also be in a probability superposition of both states. And we can see that they're all equally likely, right? So 0, 0, 0, 1, 1, 0, and 1, 1 are all equally likely, 25%. And now let's look at a different circuit. So here, both states are 0, and if we add a NOT gate to Q0, we see that our block sphere for Q0 is now 1, and we can see that also in the probability graph. And then if we add a second gate, a control gate, that means a control gate requires that the value of the bit be the control bit, which would be Q0 in this case, be a 1 in order to change the state of Q1. So we plop that into place. And now we see now the bit, they're both each in a state of 1, 1, and we can see that on the probability graph. And then last but not least, we have a Hadamard gate that we're going to put on Q0. That means we're in the probability of 0 and 1, 50% each. And now we're going to add a NOT gate for our second bit. And now we see that we're entangled. So that means that if the Q0 is 0, then Q1 is 0. If Q0 is 1, Q1 is 1. And that's how the circuit that we use to entangle these two bits to be in the probability of only 0, 0, and 1, 1 in this example. And so that's it. So there's a little bit more information in the lessons and in the app, but that's all we're going to go over today.